So what we're going to talk about today are shapes that look like this. So that would be our original shape. And this would be our image. So the green is the pre-image and the purple is the image. So what do you notice is happening between the image and the pre-image, or the pre-image and the image, I'm sorry. So here's your pre-image. So that's your original. And this guy is your image. So how could you compare? Kaleo. Okay, so in this one, the image is greater than the pre-image. Now, what else could you do to describe this picture? What else might you be able to say, Chloe?
They're the same shape.
Okay, they still have the same shape. They're both squares. Oops. What's different? Mackenzie. Okay, they have different size. So guess what we can't say these two shapes are that we could say about all the other transformations that we've talked about so far? Pete? They aren't congruent. Now there is a word that does describe them. Does anyone know what that word is? Not congruent. Okay, anybody remember that word? Well, then you might have to wait. I'm not going to play hangman on this one. Okay? All right, what we're going to do is talk about this particular notion of what occurs. This is called a dilation. And dilations either takes a pre-image and makes it larger, or takes a pre-image and makes it smaller. Okay? And we're going to talk about some vocab. We're going to go through an exercise together, and then you guys will just work on the guided practice tonight. We'll talk a little bit more, and then we'll also, you'll have a little bit more homework on this tomorrow. So let's go to the official beginning of our notes. I'm going to go off this screen for a moment, and we'll come back to it in a little bit. So our objective today is to understand dilations and associated vocabulary, and you're also going to create dilations. Oh, I keep doing that wrong. And in addition to creating dilations, we're going to determine how a dilation was made. And we'll get into that. Now, I do want to give you a couple places that online you can get some extra practice. So remember we talked about Personal Math Trainer. So you have to log into the book. And on page 320, it's going to specifically deal with the third objective, which is dealing with the notion of scale factor. And then they always seem to put one on the independent practice, and I think that's more of an overall review of what we're talking about. So remember with the Personal Math Trainer, you can go in and it basically gives you practice problems, and then with the practice problems you can they give you explanations if you're having trouble understanding something, and so you can help yourself learn how to do all the homework problems. Okay, so if you ever say, I didn't get how to do that, then you need to tap yourself into looking at the Personal Math Trainer. So we have some vocabulary that we need to understand, and first thing we're going to have is obviously the word dilation. So it's a transformation where the image is the same shape but not the same size as the original / pre-image. So dilation is a transformation. So we're changing our shape somehow, where the image is the same shape but not the same size as the original or pre-image. Now with all of our transformations, we did our transformations over something. Sometimes we were doing it over an axis, like with reflections. Sometimes we did it around the origin, like our rotations. The only one that really didn't do it around something was the translation. Okay, this one also has a point that the dilation boils down to, and that's called the center of dilation. So the center of dilation is a fixed point let's see how to say that. It's a fixed point where the lines connecting corresponding parts intersect. Okay, so a center of dilation, and when we do our dilation, you'll see what I'm talking about. I'll draw those in. The center of dilation is a fixed point where the lines connecting corresponding parts intersect. So I have an example I want us to do, and you guys are going to have to draw, and you're going to have to draw as accurately as possible, so you don't have your graph paper there, so do your best. I'm going to give you the information so that if you aren't sure what it looks like in your diagram, at least you have the hard, cold facts in a chart. So I think I'm going to start with the chart at the top, and then I'll add the graph underneath. So here's what our chart's going to look like. It's going to say vertex, and then it's going to say X, and it's going to say Y. It's going to say vertex, and then it's going to say X, and then it's going to say, oops, Y. And then it's going to say ratio. Oops. Of x's. And what we're going to do is we're going to take the dilation, the image, and we're going to put it in ratio with the pre-image, the original. And we're going to be doing a four-sided figure. And the vertices are going to be A, B, C, D. So the dilation is going to be A prime, B prime, C prime, D prime. And to do a ratio is the same way as saying a fraction. And then we have a ratio of y's. And again, A prime, B prime, C prime, D prime. And we're going to divide by A, B, C, D. So we're going to have vertex A prime, B prime, C prime, D prime. We're going to have vertex A, B, C, D. So I'm going to add my graph paper below, and as I'm drawing my object, I'll go back in and fill the numbers, okay? So let's see, what do I need to go to? Looks like 5. So you need to have a graph that goes 5 right, 5 left, 5 up, 5 down. And you label X and Y on your axis. You put tick marks in. Oops, that one's going to need to go a little further. And you're going to need to at least number every other tick mark. And I usually do the evens myself. Don't forget left and down are negative. And let's start with the image. So our image, -2, 5, that's going to be our A. Our B is going to be at 4, 2. Our C is going to be at 4, -4. And our D will be at -4, -4. A's at -2, +5. So I've got it in the chart and here as well. Joy. Ratios of x's, and then the last column is ratio of y's, and then we're going to take the image that we get when we dilate and divide it by our original one. Okay, so that's where the A prime, B prime, C prime, D prime comes from. So we're going to connect this up. And we would just call this guy a quadrilateral. He has 4 sides. There's nothing special about him. Okay. So for my A prime, we'll do him in green. We're going to put A prime at -1, 2.5. So that's halfway between the 2 and 3 mark. So -1, 2.5. And my B prime we're going to put at 2, 1. Oh, sorry, that's A prime. This is B prime. So 2, 1. My C prime is going to be at 2, -2. And my D prime is going to be at -2, -2. So you can see that they're the same shape. They're both quadrilaterals. You can see that the dilation is smaller than the original. And now what we want to do is see if we can figure out how much smaller it is. So what we're going to do is take the ratio. And the ratio says take your x's, take your x from A prime, and divide it by the x for A. So what's -1 divided by -2? Not 2. Not 1. Not -2. Not 2. Wow. 2 negatives make a +1/2. Or, as a decimal, we could write it as 0.5. Okay, next we've got the b prime divided by the b on the x's. What's 2 divided by 4? 2 divided by 4.
25.
No. You guys are scaring me. Okay. It's 0.5 or 1/2. What's c prime divided by c on the x's? What's 2 divided by 4? 0.5 or 1/2, same as the one before. And then what's negative 2 divided by negative 4? 2 negatives make a positive. So again, that's kind of interesting. All right, well, let's look at the y's. 2.5 divided by 5, which would be the same as 25 divided by 50, which would equal what? 1/2. Or again, 0.5. All right, and then on the y's for b's, I have 1 divided by 2. Well, that's easy. It's already 1/2 or 0.5. We have a negative 2 divided by a negative 4 on the c prime versus c. And that, again, 1/2 or 0.5. And then for the d prime over d, negative 2 divided by negative 4, same thing we just had. And we get 1/2 or 0.5. This is what we expect from a dilation, is that all the ratios of all the corresponding coordinates of each vertex is going to be the same ratio. If it's not the same, then we haven't made the same shape. So all ratios in dilations are exactly the same. Now, I used a word earlier in our title that describes what a ratio is. What's the word that I used earlier that would describe ratio? Look back in your notes, the objectives. What would possibly mean the same thing as these ratios? What do you think, Elijah? No, that dilation is the act of taking something and making it smaller. Cleo? Nope, that wasn't in our title. It was written as one of our 3 objectives. I think it was the last one. Oh no, I'm sorry. It's in the personal math trainer. First one. What's the first personal math trainer about? That's exactly what we're dealing with. Okay. So the scale factor determines. Let's do this. I'm going to do this. Can I move? Are we good? Everybody get everything copied down?
Yeah.
Okay. I'm going to go to scale factor on the next page. Let's go back to plain. So a scale factor is the ratio of the image to the original. It can, let's deal with the 2 different kinds. And by the way, you guys have seen scale factors for years. Where have you been seeing scale factors for years? No, number line is not a scale factor. Number line is a number line. Nope. Kind of close with the idea of graph paper, though. I'll give you a hint. Core class. Where? Not timelines. That's just a line. Scale factor is telling you how to change the shape of something. I can't hear. Rochelle, say it louder. I couldn't hear you. What did you say? Okay. No, now you're thinking about something else. That's not generally what we're talking about in too much in core class. You guys never look at maps of places? Oh, sure you were. Okay. Okay. The problem is, if somebody wants to know the distance from here to New York and look at a map, we can't look at a map that's real size from here to New York. It's impossible for us to see that. So they have to take it and they have to shrink it so it'll fit on a page. But they have to tell you how much they shrunk it by, so they give you a scale factor on the bottom, right? And they'll say 1 inch is equal to 100 miles. So then you have an idea of, oh, if it's 3 inches from here to here, that's really 300 miles. So you have seen scale factors when you're looking at maps a lot, okay? Now most of those, all the maps there are taking a shape that's large and making it smaller. That's called a reduction. So again, a reduction is creating a smaller figure. And sometimes when you're looking at really, really small things, like let's say in science you're looking at molecules, it's too small for us to see with our naked eye, so they make it larger, okay? That's called an enlargement. Where we're creating a larger figure, okay? And if you think about it, our eyes on a daily basis are performing dilations. Okay? The pupil in our eye dilates according to the amount of light. When I walk into a bright room, what happens to the pupil of my eye? Pete. It shrinks and gets small. And the reason is, if it was large, I would be blinded by the light. So it gets smaller so I can tolerate the light that's here. What happens when I walk into a dark room? What goes on with my pupil? It gets bigger, okay? And that's for you to grab whatever little bits of light that you can find so you can see. So think about it. You walk into a movie theater. They've already started playing the previews. You can't see anything when you first walk in because you've walked in from a bright lobby into a dark theater. And so you close your eyes for a moment, you open it up, and that closing your eyes allowed your pupils to get larger so that at this point you can grab any of the light that is in that darkened room so that you can now see the path well enough to walk and to find a seat to sit in. Okay? So think about that next time. That happened exactly to us when we went to the movies over vacation. Okay? So this idea of scale factor, we did it backwards. We determined the scale factor by comparing each of the x-coordinates for the corresponding vertices. Now, if I wanted to go the other direction and just give you the scale factor, how would we do that? Let me go back and show you one more thing. Remember how I talked about there's a point of dilation? If I draw a line that goes through my corresponding vertices, what is the point of dilation? Or what do they call that again? The center, of dilation. What would it be in this particular one? Where do they all go to? They go to the origin. So the origin is equal to the center of dilation. Okay, so the origin turns out to be the center of dilation. That's what they're talking about on these. And if you kind of visualize this could actually be three-dimensional, and that point is coming out of the surface, okay, like a pyramid. And that point's coming out at you. So you're looking at your shapes. Alrighty. Can I move on? Everybody got that? Okay, last little bit. So what if I want you to figure out a scale factor? What you're going to do is you're going to take your two shapes, just like we did, is you're going to take the ratio of each coordinate that corresponds, and you're going to do the new guy over the old guy. So this is called the image. In our case, he's the actual dilation, and this guy is the original figure. Now, it could be the ratio of each coordinate like we did before in that chart. So we got the x coordinate of the a prime and the a, divided them and figured out what the ratio was 1/2. And we could do that so on and so forth. We could do the ratio of the length of each corresponding side. So we could take an entire side, a prime, b prime, what its length is, and put it in ratio with the original length of that corresponding side. So there's different ways to find the ratio itself. Now I believe what we get to do in our next one is be given our scale factor, and then how would our image look from that. So we could create it just knowing the scale factor. So we'll deal that with a different lesson.